So sometimes it's very difficult to set up a region as an elementary region the way that we've been looking at before, and it's much easier if you think about it in terms of polar coordinates. So in this example, suppose we've got this integrand here, e to the minus square root of x squared plus y squared, and we're looking at this domain right here. So we want all the points where x squared plus y squared is between 1 and 4, and we want the x coordinate to be non-negative. So let's decode this region and kind of figure out what it looks like. So if I just look at this part right here, that boundary x squared plus y squared equals 1, that's the unit circle. And then if I look at this part right here, x squared plus y squared equals 4 is the circle of radius 2, which is the outer boundary of this region. Okay, so that tells us that we are looking at this region right here. So we are looking where x is non-negative, so we're out here on the right half, and then we're going to be between these two circles. So we're looking at this patch right here. And now let's see, so how am I going to set this up as an integral? Well, that's kind of nasty, right? So either way I go to try and set this thing up, it's going to be a royal pain. So let me just duplicate this figure, and then we'll talk about how to do it each different way. So on the one hand, we could talk about integrating, let's see, maybe dx first. So if we're doing dx, then we're going to be starting on this smaller circle and going out until we hit this outer circle, except if we're sufficiently high or sufficiently low, in which case we're going to be starting on the left with a vertical line and then ending on the right with that outer circle. So we actually would have 3 elementary regions, one up here, one down below, and then a purple one in between that goes from circle to circle. Okay, now what if I did things the other way? So if we were going to go vertically like this, so we do the dy first. Well, it's not much better, right? Because we're going to be starting on the outer circle and ending on the inner circle, or else we're going to be starting on the inner circle and ending on the outer circle if we're in one of those zones, or else we're going to be starting on one half of the big circle and ending on the other half of the big circle if we're in that purple zone out there. And in any of these situations, we're also going to have to contend with this obnoxious jerk of an integrand, which is not going to be easy to work with. It's just an ugly mess. But there's a better way. So the thing to do is notice that these boundaries are radial lines. So in other words, lines passing through the origin like this. These are radial lines. And in particular, the radial lines that we're seeing are this one is the one that shows up bounding the figure that we're looking at. Boundaries are radial lines and concentric circles. Right? So we've got things like that are looking like this. And these concentric circles, these are examples of where the radius takes a constant value. So we might have r equals 1 on this innermost one, and then maybe this next one out here is where r is equal to 2, and then this next one out here, pretty bad circles, I know. That's r equals 3, and so on and so forth. Meanwhile, if we go back to the radial lines, these radial lines might correspond to theta equal 0 in polar coordinates, and then something else might be, where theta is equal to pi over 6. This one that we're actually interested in, here, let me make it purple, is where theta is equal to pi over 2. But anyways, so these radial lines are where theta is equal to a constant, and these concentric circles are where the radius is equal to a constant. And so the fact that we're seeing a region bounded by radial lines and concentric circles is this problem screaming at us that we should use polar coordinates to set it up. Okay, so going back to this region of interest here, let's see. So as we just mentioned, we're going to be looking at this one right here, which is where the radius is equal to 1, and this one right here, which is where the radius is equal to 2. And then we're going to be considering this from where theta goes from minus pi over 2 all the way around to where theta equals positive pi over 2. Okay, so I can actually set up this region as the integral minus pi over 2 to pi over 2 and 1 to 2 of my function dA. And there's a couple things to notice about this. First and foremost is the fact that now we are actually looking at a composition of functions. So polar coordinates, this is where you take x to be r cosine theta and y to be r sine theta. So in particular, we're thinking of x now as a function of r and theta, and we're thinking of y now as a function of r and theta. And so our function f is now fundamentally a composition of functions, and at the base of it, it's a function of r and theta. So this is going to be, let's see, so we've got e to the minus x of r theta squared plus y of r theta squared square rooted. And so this, in terms of the polar coordinates, let's go down, is e to the minus square root of, let's see, so x was r squared cosine squared theta, and then y was r squared sine squared theta. Well, sorry, y was not that, but y squared is equal to that. There we go. So that's this thing. And if you factor the r squared out and you use the identity cosine squared plus sine squared equals 1, we get e to the minus r. Wow, what an improvement. So that's like another hint that this is a much better problem to set up in terms of polar coordinates. All right, so now here's the thing. Let's take a little bit of a closer look as to what's going on. If we have the r theta plane, and then we're transforming by polar coordinates, right? And then from that, we're getting this region of interest. And then here we've got some function f that we're integrating. So you can see that this is the way the composition is set up, right? And so we've got R going from 1 to 2, and theta is now going to be going from minus pi over 2 to pi over 2. So say this is like minus pi over 2 and pi over 2. Look at that. It's a rectangle. It's a rectangle. So we're actually secretly integrating over a rectangle when we use this change of coordinates. But actually, you knew that this was a rectangle because you saw me write down this expression right here, and you saw that these bounds here are all constants. And we talked about before how that's the hallmark of this being an integral over a rectangular region. Okay, so we're integrating over a rectangle. No wonder it got so much nicer and so much simpler. Okay, now the only thing is, when we take this rectangle here and we transform it and make it into this right here, so imagine this happening in slow motion, right? What's happening? So this rectangle is being like slowly warped, and then like warped even more until it comes out looking like that, right? Now the part that is being that's sort of on the outer side here, this is getting stretched out. It's getting longer and longer and longer as we go around. So there's a deformation, there's a change of area there. And we need to account for that somehow. So just like when you do a U substitution, so that's a change of variables as well, where you're reparametrizing by saying, oh, x is actually going to be some function of u. Then you have to take into account by chain rule the du term, or else your U substitution goes all to heck, right? So we are going to have to do the same thing here. And so for to account for area distortion, under composition, we need what's called the Jacobian. And so the Jacobian is written as dxy over, or partial xy over partial r theta. And it's actually a matrix. And so the way we set it up is we put the partial of x with respect to each of the independent variables, so dx dr, dx d theta. So the first function gets the first row, and then the second function y gets the second row. So dy dr dy d theta. And then we're going to take the determinant of this matrix. So in this case, we're using polar coordinates. So x is r cosine theta, and y is r sine theta. So let's see. So our first derivative is going to be partial of x with respect to r. Oops, partial of x with respect to r here. So that's going to be cosine theta. And then we're going to have partial of x with respect to theta, which gives us minus r sine theta. And then for y, the derivative of r sine theta with respect to r is sine theta. And the partial derivative of r sine theta with respect to theta is r cosine theta. Now we need to take the determinant. So the first term is the product of these ones, r cosine squared theta. And the second term is the product of the off-diagonal terms, which is minus r sine squared theta. And you subtract the purple from the green. So we have r minus negative, oops, forgot my stupid cosine. R cosine squared theta minus negative r sine squared theta. And so if we factor out the r, again by everybody's favorite trig identity, aka the Pythagorean theorem, we get r. So there's a distortion factor of r. And you can in fact see this if you go back to looking at what's going on. Let me draw some radial lines here. So if we have oh, come on, there we go. Now, suppose these are all, oh gosh, that was crazy. That's just a testament to how bad my circle was. Okay, now suppose these are all equally spaced concentric circles. I know it's not really looking like that, but whatever. Then notice that the little infinitesimal area, like if you imagine cutting something up for Riemann sums or whatever, if you're between these two values of theta, so here like theta 1 and theta 2, then the region close to the origin is much smaller than the region out here further from the origin. And in fact, the area of these little boxes increases linearly with r as you go outwards. And so that r, that's exactly what this r is right here. So it's taking into account this distortion that happens where the little patches of area that are further from the origin are getting stretched out larger and larger. And so this is our du term. So when we set up this integral, whoops, what have we found? Well, in the r theta plane, theta goes from minus pi over 2 to pi over 2, and r goes from 1 to 2. And our function, we saw, is now going to be e to the minus r. And then we need our Jacobian determinant, which is just r. And then that's integrated dr d theta. And now there's an integral I know you can work out. So the key takeaway from all this, aside from how to set things up as a composition, is that we do not need to repeat this computation every single time. We've done it once, now we have it forever. And so what we know is our area element, which previously we were writing as dx dy, or as dy dx, in polar coordinates, it looks like r dr d theta. So that's kind of new. That's coming from the Jacobian determinant. So you just have to remember that when you set things up in polar, you always remember to include the r with your dr d theta. It's possible to have an integral that's r d theta dr, but we're not going to do that in this class. In practice, it like really doesn't come up.